call it. In MITEI, he oversees a large portfolio of research projects across the spectrum of issues and challenges that we are discussing at the conference. He has been a faculty member at MIT since 1973, working on energy, materials, and fluid mechanics. And before he came to MITEI, he was the head of the chemical engineering department. He has a very prominent research record with many awards. Let me just mention that he was elected to the National Academy of Engineering in 2008 for his work on non-Newtonian fluid mechanics. I don't know if we'll hear much about that in his presentation, but looking forward to hear what he's going to say about the global energy challenge and what's ahead. Bob.
Is there a lavalier mic I can use? Good evening. It's a great pleasure to be here to talk to you about some of the work we do at MITEI, which is MIT, in energy. And I'm going to talk to you in the context of what is the global energy challenge and what do we see on the horizon. It seems to fit with the A plus B theme here at the conference, looking at energy and looking at some of the new technologies coming down the road. I'm going to get down below in a minute just because I need to point at a few of the slides in a few minutes, and I can't do it very well from here. So I'm going to start off with what MITEI is about, which is addressing the global energy challenge, which I describe as these 2 points. The first aspect of the global energy challenge is that we're facing substantial global energy demand growth over the remainder of this century, more than doubling energy demand. That's the projection. Driven primarily by developing countries as residents of those countries improve their standards of living, as GDP rises, as population rises, they will require energy to meet those needs. The second aspect of this challenge is that we need to decarbonize the energy system. So we're looking at a more than a doubling of the energy system done carbon-free and also removing carbon emissions from the system we have today. So it's a really large challenge in front of us, and it's a challenge that needs all disciplines on hand. It's not a challenge, it pains me to say this, that won't be solved by engineers alone, but we need to have economists involved, we need business experts involved, we need science clearly involved, we need architects, urban planners involved. And that's been part of the goal of MITEI, is to bridge across all those disciplines and see how we can bring different ways of thinking together to make faster progress on these big challenges. To highlight the challenge and the timescales we're looking at, I have this plot, which many of you have seen probably, but it's good to remind ourselves that time is short. This is a look at CO2 measurements made on Mauna Loa. And you can see the steady rise in CO2 concentrations as years pass. And you can see if you blow that up towards the later years here, you see the oscillations in the annual cycle between the spring and fall, summer and winter. What's striking here is that back in 2016, for the first time, we passed, for the first time in millions of years, we passed 400 ppm CO2 in the atmosphere for the whole year. Earlier this year, in April, for the whole month, we averaged a little over 413 ppm. So we are moving right along on this curve. If you make a very simple linear extrapolation, which is a very conservative way to do this, but if you extrapolate the rate of increase, say from 2010 towards today, out in time and ask when does that cross 450 parts per million? And I picked 450 parts per million because that's the nominal concentration that's often associated with a 2-degree scenario. And it turns out that this simple extrapolation intersects 450 ppm around 2037. And that's not very far away, right? So by 2037, we will have saturated what we can afford to put in the atmosphere. And so the message there, and a recurring theme through this talk is, we're doing some really interesting things, but we need to go a lot faster. And there's cooperation and collaboration as key elements. To put a little detail on the challenge ahead, I have some plots here that come from the Joint Program on the Science and Policy of Global Change here at MIT. It's a wonderful program that actually started back in the early 90s, about 1991, I believe. Brings climate science together with global economic modeling and provides tools like the model used here that allow you to look at policy scenarios. Take a policy scenario like the Paris Accord and ask, what are the implications of that for concentration of CO2 in the atmosphere or greenhouse gases in the atmosphere? What is the impact of that on global warming? What's the impact on economic growth, trade across nations, and so on? You can run lots of different scenarios. The scenario I show here is a scenario which assumes that the 190 or so countries that signed on to the Paris Accord in 2015, that all of those countries meet the commitments they made then, but we don't do anything else. So at the end of their meeting those commitments, they just maintain in steady state at that point. And some of those commitments go out to 2025, some to 2030, but whatever point they hit their commitment target, they just stay at that point. What you can see is that with the Paris 2015 agreement, commitments made, that we have a more than doubling of energy by 2100 from some 500 exajoules a year up to 1,050 maybe exajoules a year. So that's one point, is that we still see substantial growth in total energy use. Second point is that if you look at around 2050, you see that we still depend dominantly on fossil energy resources, coal, oil, and natural gas. They make up about 75% of the primary fuel mix in our energy system. In getting to the Paris commitments, there's more gas and less coal in that mix than in a business as usual scenario. But nonetheless, the dominant source of energy on the planet is fossil, right? So that's a challenge for us, and it points out that the critical nature of doing more than Paris. And of course, that's the plan in the Paris Agreement, is to ratchet with time. But we need to get on with that if we're to be doing well by 2037. This is a breakdown of that plot, the previous plot, by different sectors of the world, organized around developed countries, so North America, Europe, Japan, South Korea, and so on. The other G20 countries, China, India, Brazil, and so on, Africa, and the rest of the world. And what you see there is the absolute importance of doing this globally, right? The predominant growth in energy use and CO2 emissions occurs not in the developed countries, but in developing countries, like China, like India, and so on. So we have to figure out how to provide technologies that are cost effective, that they can deploy at scale. If we look at a plot like this is an IEA plot that looks at past CO2 emissions up to today, and then at a couple of scenarios that go beyond today, a business as usual scenario, the red curve at the top, the Paris Agreement solution, which is the one COP21 in gold. There's a green curve, which is a 2-degree curve, and then a 1.5-degree curve in blue. Those get increasingly more difficult to meet as you go down there. Now, it's important to remember that energy is used in all sectors of the economy, and so that set of composite curves at the top are broken down by sector at the bottom. And in this talk, we're going to focus on the electricity sector, just to pick that because it's been the one that's been focused on mostly in decarbonization today, in part because it seems simpler to go after large point sources of CO2 emissions and change those as a first point. And the idea has been that once we decarbonize electricity, then we'll shift in and electrify other sectors. And I'll argue that if 2037 is when we hit 450 ppm, we cannot afford to do this sequentially. Right? We're not going to be able to have the luxury of time to do electricity, then transportation, then industry, and so on. But we're going to have to start working in parallel here. And that's a change, I think, from the way we've been thinking over the past 10 years. We've been making good progress. There's been a lot to be proud of in the global activity in driving CO2 emissions down. This plot is a look at progress in driving solar and wind costs down. This, in particular, is a solar chart looking at the PPA costs, the power purchase agreements that have been signed in the U.S. Over the last maybe 10, 12 years. And the message there is simply that the prices have dropped dramatically over that time from something over $200 a megawatt hour, which makes solar a very, very expensive way to get electricity, down to 2018, where the average PPA was $26.1 per megawatt hour, which makes it the cheapest electricity capacity to add in the world, right? So solar has become a very attractive way to provide new electricity capacity, particularly if you don't have a lot of solar. If you have a lot of solar, you run into system issues, which we'll talk about in a little bit. So good news there, these prices dropping rather dramatically. And we've seen examples, for example, in Tucson, of solar projects that have had integrated storage, not fancy storage, lithium-ion battery storage, to give a 100 megawatt power plant with 4 hours of 30 megawatt storage, all at about $45 a megawatt hour. So very, very cost effective and dispatchable. Investments in solar and wind have been rather dramatic around the world over the last 12 years, as this plot shows. What's really interesting is to look at the projections of solar and wind additions over the next 30 years. Projection is about $8 trillion of additions in solar and wind. That comes out to about $750 million a day for the next 30 years. So massive capital investment in these technologies, driven by the fact that they're cheap technologies, a cheap way to add to capacity to meet human needs for energy. I'd like to make the point that solar is not alone. Solar and wind are not alone in benefiting from technology, in dropping costs. At the same time, we've experienced, particularly in North America, we've experienced the shale oil and shale gas revolution. That started in the early 2000s, around 2005. You started to see the impacts of technology development that had gone back multiple decades. Probably 40 years worth of research funded early on by government, work on rock physics, rock fracturing, horizontal drilling, but then picked up by the private sector and demonstrated and driven to the point where it could scale. Back in 2000, I think very few people thought there was any way you could get gas out of rock that had such small pores as shale rock. But what you see, if you look at the production increase in the major shale plays in the U.S., I'll give as an example this medium blue colored slice in the middle is the Marcellus shale. That's the shale play that runs into the northeast, Pennsylvania, West Virginia, parts of Ohio, New York. That was not thought of as a big gas production zone in the U.S. Back in 1990, say. Today, the Marcellus alone, if it were a country, would be the world's third largest national producer of gas, right, behind the U.S. and Russia. Right? And that's just a region in the U.S. of shale gas. So this has made an enormous difference in the availability of gas and affected gas prices in the U.S., but it's also affected gas prices globally because it's produced an excess of gas in the U.S., low-price gas in the U.S. that could be liquefied and shipped as LNG. So you see gas prices in places like Japan that have dropped by a factor of 3 from 2008 when they had long-term contracts for gas. One of the impacts of these low gas prices driven by shale production techniques, fracking technologies, is that natural gas has displaced coal as the largest fossil energy source of electricity in North America. And it's happened simply because of price. Right? The economics have driven that change. And as much as some politicians like to think that it's been driven by policy, it has not. And this is the story there. Natural gas in the U.S. has accounted for the largest fraction of decrease in CO2 emissions. We have about a 17% drop in CO2 emissions relative to 2005, which I think puts us ahead of the pack globally in terms of CO2 emissions drops. And this is a big factor there, this displacement of coal. One of the side effects of displacing coal is now that CO2 emissions have dropped fairly dramatically in the power sector is no longer the largest CO2 emitting sector in the U.S. It's transportation today. So that's to reinforce my message a minute ago that we need to be working all sectors now at the same time, not trying to do this sequentially. Some of the challenges in having large penetration of renewables, I'll illustrate here. Most of the world has very small penetration of, say, solar, just 1 or 2% of solar. Some regions, Hawaii, California, have significant penetration of solar today. California around 15, 16% solar. This is a look at day-ahead markets, locational marginal prices in California. And if you look at this one slice in March and blow up and look at the price of electricity over a day plus period, interesting thing to note is that the price goes negative. Right? So one of the impacts of very cheap solar in a region like California is that you have so much zero marginal cost electricity bidding into the system that the clearing price goes negative. Right? In this case, that's driven by natural gas combined cycle producers who want to keep their plants running while solar is producing so that they're ready to ramp up rapidly in the afternoon hours. And so they're willing to bid in negative in order to do that. So clearly we have done well with solar, with wind, with natural gas, but there are big challenges ahead in all of those. With solar, we have the challenge of technology that produces when the sun's out, but clearly it's going to need to be displaced off of peak solar hours. With gas and with shale oil, we have the challenge that eventually it has too much carbon in it too, right? So we have to figure out how we get from natural gas as it is to a carbon-free solution. To look at this at MIT, we have been focusing at least some of our efforts around 8 low-carbon energy centers. And the idea here has been to bring industry together with faculty from multiple disciplines to look at how can we reduce carbon emissions from fossil resources, CCUS technology. How can we take energy bioscience to look at, among many things, negative emissions technologies so that we can come back if we overshoot 450 ppm, which we almost surely will do. Energy storage technologies, key for being able to displace solar to times when it's needed, same for wind. We have solar energy, need to make that cheaper yet so that it can be deployed readily in developing countries with much lower balance of system cost. And then we have some dispatchable zero carbon technologies, fission, which is really the only dispatchable zero carbon technology we've had at scale globally, and more recently, fusion. And at MIT, the principal fusion activity a year ago spun out as a startup company, Commonwealth Fusion Systems, and so we've X'd this one out now and replaced it with mobility. So focusing on the transportation sector. So we have 2 integrated systems, one electricity and the new one here, mobility, aimed at understanding how all those different technologies we're developing, how they come together and work together to give you the services that you want out of those components. At the end of the day, consumers really don't care so much about where electrons come from. You just want to flip the light switch and have the lights come on, or reach in your refrigerator at the end of the day on a summer and make sure there's a cold beer in there and it's not room temperature. Right? So it's the service that matters, particularly in a commodity business like this. So let me give a few examples of the importance of working in those areas. First one I'll refer to here is looking at what negative emissions technologies might do for you. Right? So from that graph I showed earlier of CO2 measurements on Mauna Loa, it's pretty clear we're going to go past 450 ppm. So we're going to need to have some way to get back into livable territory. One way to do that is to grow biomass and then burn it and capture the CO2 and sequester it, right? So-called BECCS energy, so bioenergy plus CCS. This graph looks at a future global electricity mix in a 2-degree scenario. That is, we assume there's a price on carbon that's sufficient to keep us at 2 degrees. And look at how that future would develop when there's no negative emissions technology, no BECCS, say, and if we do have BECCS available. First thing I'd like you to notice is that if you have BECCS available, negative emissions technologies, we end up using more energy. We can afford to use more energy because we can deal with the CO2 emissions. Second major difference is, of course, there's a lot more biomass in the energy mix in this system. Not obvious from what you see here is what price on CO2 would you have to put in order to get 2 degrees in these 2 scenarios. In the case where you allow BECCS, you allow for negative emissions technologies, by 2030 you would have about a $70 a ton price on CO2. By 2050, that would go up to $100 a ton. By 2100, that would go up to $300 a ton with negative emissions technologies. If you don't have negative emissions technologies, in 2030, the price would be $200 a ton, much worse than the 70. By 2050, it would be about $350 a ton. By 2100, around $900 a ton. So if you don't have negative emissions, you're going to have to apply severe economic penalties on any emissions technologies. So that leads into a profound interest in how you can capture CO2 more cheaply and more effectively than we do today. I put this up here as an example of many research programs around the world looking at lower cost ways to do this. In this technology that's developed by Alan Hatton in chemical engineering, he looks at a way to take traditional amine capture technology, so something we understand really well, but make the desorption process, the release of the CO2, much less costly. And he does that by adding a third species to the system that is more attractive to CO2 under certain electric field conditions. Efficiency is a really important part of going forward and reducing emissions. We have today about 85% of the world's power is made in thermal power plants. At the back end of every one of those power plants is a condenser, right? You'd like that condenser to run as efficiently as possible, and a mechanical engineer here at Kripa Varanasi and a chemical engineer, Karen Gleason, worked together with their students to develop a way to coat condenser surfaces so as to force dropwise condensation. And for reference, having dropwise condensation versus filmwise condensation gives you an improvement in heat transfer coefficient of a factor of 7. So it's a big, big difference. And that translates into the overall efficiency of the plant into a couple of percent. Now, 1 or 2% maybe doesn't sound like a lot, but if you apply that to 85% of the world's electricity production, it's a big, big number. So efficiency, really important. Another look at efficiency is how can you avoid using so much water in cooling these systems. This is another example from Kripa Varanasi, a technology, a startup company now they call infinite cooling. And what they do is to capture the nucleated water droplets coming out of the cooling tower. They apply a static charge to them and capture them electrostatically. They believe they can get about 90% of that water recovered, so it can prevent you from having to use fresh water for the cooling process. If you happen to have a coastal power plant that's using salt water, you get distilled water as a result of this process. So you can get power plus drinking water for residents. This is the dome that they've made for capturing the water, and this is it being installed at MITEI's power plant on one of our cooling towers. And this is a nice example of how MIT uses its own campus in order to try out new ideas and use us as a pilot plant for new technology development. We have exciting work going on in how you bring AI methods, machine learning methods, to materials discovery. These are two faculty, Elsa Olivetti and Stephanie Jeglica, looking at how you can accelerate discovery of new materials for, say, batteries. By looking at, before you start spending time and money in the lab synthesizing materials, how can you estimate accurately which ones could be scalable? And of course, scale is of paramount importance in energy solutions. This is a look at work done at MIT in Vladimir Bulovik's lab with the lightest weight solar cell ever made. That's it floating on top of a soap bubble. Probably need a different installation infrastructure out in the field, but that's the proof of lightness. At another extreme, this is a picture in the bottom left, is a demonstration by Katie Taylor, one of the Tata Center students a couple of years ago, showing a solar-powered irrigation pump to newly re-elected Prime Minister Modi. It's a device that uses a much lower power irrigation pump that can be powered by a single solar panel, which a rural farm in India can use, and there's about 35 potential customers there. And has a payback time of a year relative to trucking and diesel, which is the way they had been doing it. So very attractive technology. Interesting work in grid-scale batteries is Yetming Chang's group that formed a group called Form Energy, looking at flow battery technologies. Don Sadoway, very interesting technology using liquid metal components for another grid-scale battery. And this is a look at the scale of the fusion reactor that Commonwealth Fusion Systems, this spin out from MIT, that it is focused on building and testing at scale in 12 years from now. So not the 35 years that it's usually been, but now starting to see a shrinking time horizon. One of the things you notice here is that people aren't so small relative to the size of the reactor, which is one of the keys to this reactor. It uses high temperature superconducting magnets, which allow a much smaller scale. So that's a really exciting development to follow. And then lastly, and I said at the beginning that developing countries were key here. This battle is going to be won or lost in India and Africa, I think, as those economies grow. And so we have got to figure out ways to bring low carbon energy to meet growing GDP and quality of life needs in those countries. One of the ways we address that at MIT and at MITEI in particular is through the Tata Center for Technology and Design. It's a center that's focused on how do you go into a developing country like India and look at unmet market needs for which then you develop a technology-based solution. So that requires engineers to figure out, and engineers and science to figure out how do you design something that meets the market need but recognizes and is consistent with the constraints of economics, with supply chain constraints, with human resource constraints, with policy constraints. In other words, that can actually be deployed in the markets. And we have had about 50, 60 students per year going through this program. And it's been very successful at spinning out companies, startup companies, to provide these services. Over the last year, there were, as I understand it, 22 startups that were student-led startups. 7 of those were out of the Tata Center. We do startups in energy, obviously, from the Energy Initiative, but it's interesting, they also do startups in health, agriculture, water as well. And so it's been a very exciting program. So with that, I'm going to stop with just a brief reminder to you that time is short. Right? 2037 is what you ought to think about. We need to go faster. We need to go in parallel across sectors. We have to go at scale, to the global energy scales. And we have to work with each other across the boundaries of disciplines, across the boundaries of academia and industry, across the boundaries of academia, industry, and government, and most of all across geographic boundaries around the world. So thank you, and I look forward to all the new things you invent that are going to get us there by 2037. Thank you.
Okay. Do we have any questions for Bob?
Thank you. I'm Sarah Jordan. I'm a professor at Johns Hopkins University. My question is something that I'm concerned about, and I'm interested in your opinion. So a lot of the time, we're all here because, well, I hope that everybody cares as much about the planet as I do. And we are in a bit of trouble, right? We had this economic system moving, and we have the 1.5 degree IPCC report that came out. My biggest concern that I've heard lately is that there are a growing number of students and young people who say, well, we're just not going to get there, so we should just worry about adaptation. And I don't think that's the right answer, because carbon accumulates in the atmosphere and the problem continues to grow. So if we keep on saying we have a big problem, we have to get there, and we don't continue to remind people that it then gets worse, then I think we have a bit of a political problem. So I'm interested in your insights about how we can encourage people that, okay, maybe if we don't meet 1.5 degrees, it's still that important. So given the nature of this conference and that we all care about this issue, I think it's extremely important that we all keep that in mind. So I'm very interested in your thoughts, and thank you for your talk.
So I agree that we need to give people hope that the world will be livable. We have not been doing a great job up to this point of living up to our responsibilities for the planet. And so I can see how young people would get a bit discouraged. What I tried to point to here, though, is that even if we go past this 450 ppm, what's critical is that we have in our toolbox technologies that could be employed to bring us back. I think many people have been reluctant to talk about negative emissions technologies in the past for fear that then the government and the public would say, well, what's the problem, right? We don't need to eliminate emissions. We'll blow by and then we'll come back later. It's going to be a really, really hard problem to do that way. The sooner we can decarbonize any part of the system, the better off we will be, right? But I think we need to have as many different arrows in our quiver as we can in going after this problem. I think you can't ignore adaptation in the sense that I think it's unavoidable. My home state is Louisiana, and it's probably at the very front of the battle here in terms of losing land to sea level rise. And states like that, states like Florida, I think have to start looking at ways to adapt, not just their cities and living areas, but their economies as they go forward. So I think some adaptation, but we cannot take the view that it doesn't matter what we do with decarbonizing the energy system, we can always come back. We're going to need both of those to get where we need to be.
Great. Did we have one more quick question?
Dr. Aoife Foley or whatever, I'm a reader. There's no such thing here in the US, but I think you know probably what it is. I'm from Queen's University, Belfast, and a wonderful talk. We talk about decarbonisation all the time, but what about methane, NOx and SOx? What are your opinions on those, please, Mike?
Yeah. So clearly we need to I use the word decarbonization for greenhouse gases. And that's speaking loosely, I realize, but I think most people capture it more easily that way. And there's a whole suite of greenhouse gases that we have to deal with. What those challenges look like are a little bit different in different sectors, and that's a challenge. But methane, obviously, we have to get rid of in the system, methane emissions. I think a very interesting technology that seems to have finally got traction is hydrogen. And I think an interesting pathway for hydrogen is from methane, taking methane, steam methane reforming, plus CCS, and then you have hydrogen at the lowest cost possible today. There will come a time, hopefully fairly soon, when you can do electrolysis to produce that hydrogen using renewable electricity. But there's some interesting pathways there that use the methane resource we have now in abundance to do it pretty cheaply. You can do hydrogen from steam methane reforming for about $3 a kilogram. Today, if you add CCS, it's about $3.50 a kilogram, and that's competitive with gasoline as an energy source, right? So if you think that gasoline is about a kilogram in energy content, but a fuel cell is more efficient than an ICE, so it's about a 2 to 1. I think industry has the appetite to provide services to the public that they can make money on, right? I mean, so a challenge we've got is with CCS and with negative emissions technologies, there is no earthly reason you should do that right now if you're an industry, if you're a for-profit organization, right? It's a money loser. In the U.S., we have interesting part of our tax code, the 45Q. I don't know how many people know that, but it provides tax incentives for CCS. And it's actually, I think it's the highest price globally for CCS. It was in 2018, the tax code was revised in a bipartisan way, which is, I think, interesting, to provide, I think it's $30, $35 a ton for CO2 that's captured and used in EOR applications, and $50 a ton for CO2 that's captured and used for sequestration or for making materials from CO2. Just this past week, the first scale project of capturing CO2 from the air and using it for EOR that takes advantage of 45Q was announced. It's a project from Occidental. So that's encouraging, but honestly, unless we pass policy that puts a price on carbon emissions, in some way, it could be cap and trade, I don't care how, but put a price on the emissions. And then industry will have an economic incentive to go fast at this.
Okay, great. So I think in the interest of time, we have to move on. So let's thank Bob Armstrong once more. Okay, so the next